Hello again, everyone. I'm always glad to have visitors come to this channel because what I've realized is in the short time that I've been on YouTube, one thing about this is that what I've realized is you spend just a short time on this channel and you either feel great or you never get over your feelings. It'll almost kill you. And nobody ever comes here and goes away unaffected one way or the other. And I quite like that because it reminds me of the principles that I've always upheld. And actually, next week I'm going to be doing a video specifically on the principles that guide city tutoring, what my vision was when I founded city tutoring, and and the things that guide everything that the educational philosophy that I have. So, because I'm never satisfied with this business of being in second place. In other words, I'm never satisfied with mediocrity and doing things like everyone else. And that may be all right for failures, but it's not right for those of us who have a passion for math and for truth revealed. And God expects each of us to be the best that we can be. Failing a test, if you're a high school student and you're watching this, or even a college student, failing a test in and of itself is not a disgrace. But we believe it is a disgrace to do less than your best to keep yourself from failing. And that is why I have been blessed because so many of you have left comments. So many of you are very heavily invested in doing the best that you can be, being the best that you can be. Now, of course, that doesn't mean that everyone is going to become a mathematician. That doesn't mean that you're all going to be some kind of all-star. But what it does mean is that within your limitations, within your capabilities, you do the best that you can. Not everyone has to be a Mercedes, not everyone has to be a Cadillac. You're just as fine being a Toyota if that works for you. If you were made to be a Toyota, that is all you can be. We're living in a society that has taught you that you can do whatever you want, this ignoring realities, that you can believe to be anything you want, ignoring certain realities. No, the fact remains that even you should have dreams, you should have aspirations, but you should also be realistic in your physical capabilities and also your mental capabilities and all that good stuff. But anyway, that's going to be next week. This video is going to be a continuation of inequalities because we didn't even touch the tip of the iceberg yesterday. We need to talk about intervals, we need to talk about everything a lot more. So my name is, for those of you who are new to the channel, my name is Alfred Cromwell. I am the founder and president of City Tutoring. I am speaking to you from the city of Lynchburg, Virginia. And I am happy to have you on my channel. I hope that my aspiration for this channel is to make math, to defend the standards in math, to defend math as it was meant to be taught, which is with axioms, with proofs, and with just a little bit more exposure, at least, to the mathematical laws. Now, unfortunately, in this video, a lot of times I'm not able I would need to do a 3-hour video if I were doing something like a proof. And I might even just one way, because it does bother me not to prove things. So what I'm thinking of doing is I might just start a series of, just instead of solving problems, also just proving the theorems behind the problem, doing like different kinds of proofs and getting your feedback on that. But we'll see how that goes. It'll be a video series. There's just so many things to do always. And there's never a dull moment here because I'm always keeping myself busy with something. There's always something to do. If you ever find yourself bored, it means that you don't have a fulfilled life. It means that you're not doing things the right way. And if you're a man and you're watching this channel, you know exactly what I'm talking about. You have to have a purpose in life. You have to be productive. And if you're just lounging and you're not doing anything, then you're becoming a parasite. And we don't want parasites. I certainly don't want parasites around me. But anyway, here goes for the second part of the video. I've linked down the previous video below. All right, so we were discussing yesterday, we left off on a brief intro. I gave you the properties, the existing properties of inequalities. But I wanted to show you this. You need to understand this because I was using, if you recall, set notation for the solution sets. But this is extremely important that you become, if you're not already familiar with it, I'm talking to students primarily who might not be familiar with this. This is the interval versus set notation. Notice that there are different sets here, different intervals. You have closed intervals, you have open intervals, and when the solutions, for example, if you look at the interval, the first one, parentheses AB, that means A is less than X, which is less than B. So the graph solution would not include A or B. Why is that? Because it's less than, right? So A is going to be less than the value of X and the value that you're solving for. Same thing with B. Now, if it is if an equality is possible, if it is equal, then we use brackets and we can close in the circle. So just you can if you have your textbook, I hope that it has at least a chapter on this, right? This is a standard. Even today, I still see that being taught in most schools, even in the worst schools. Most of the students have a notion of this, but I just wanted to review this a little bit. Also, there's a couple more. There's one more down here, and I think actually it's the first one. So never mind. But this is the way it works. All right. So if you want to copy this or if you want to download it somewhere, they're available. The interval table. There are different ways of representing it, but for our purposes, I like this one. But let's see if we can use some of these intervals and talk about how to solve some basic inequality. I'm going to start you off basic and then we go into deeper things. But basically, if you have, let's say, just going to think of something, 3 parentheses, 2x minus 9, we're going to make that less than 9. Well, we have, first we have parentheses, so that means we obviously are going to use the distribution axiom, distributive law. So 3 times 2, I assume if you're watching this video, you're already familiar with distribution. If not, then this video won't make sense. I always like to clarify the level. So this is 6x, 3 times negative 9 is negative 27, which is less than 9. And of course, if we're solving for x, we add the 27 on both sides. So now we have 6x is less than 9 plus 27 is 36. And if we solve for x, that means that x is going to be finally less than 6. Now, the important thing is if you were to write the solution to this in interval notation, it would be negative infinity. So parentheses, negative infinity, and you would up to the 6, but of course not including 6. So a graphed version of this would be on the number line. You have a 6 here, let's say, and of course it's going to be an open circle, use red, and of course anything to the left to infinity, right? So it's going to be all the way shaded in. So that's a basic graph. I'm not the best drawer. I'm awful at drawing, which is one of the reasons why well, it's kind of a joke, but that's why I don't really do a lot of geometry problems because the drawings are just awful. But back in my day, I had to draw because my school actually you were not spoon-fed the diagram. You were given a geometry problem and you still had to draw everything that the teacher actually told you that you had to draw your own shape and everything. Then later on, they started printing them out and make them more standardized. But anyway, that's one example that you have here. The other example let's think of another one. This time we'll do -4, and we'll do parentheses 3x plus 2, and let's make that less than or equal to, I'm trying to think, 16. All right, so again, distribution principles. -4 times 3x, that's going to give us -12x, minus 8 is less than or equal to 16. Then, of course, we have -12. We're going to add on both sides the 8. We have -12x, which is less than or equal to 24. Now, remember what we talked about in the previous video, and we showed what the property behind that. When you divide and when you multiply by a negative, the inequality symbol is reversed. So now x becomes, if you solve for x, of course you divide by -12 on both sides, but x actually is now greater than or equal to -2. And we showed why that is, the reason behind that in the previous video. So in this case, that means that the negative 2, because it's greater than or equal to negative 2, that means that your negative 2 is going to be shaded in the graph because it is included as part of the solution. So your answer would be, you would just put bracket negative 2 and move it all the way. Let's see if I can get infinity. Yes, I can. All the way. So that would be in interval notation. But then if you want to graph that, and as I said, I think most of you watching this video would be familiar if you're in high school, I hope. But if you're not, let me know. Also let me know in the comment section. So this becomes, down here, we'll put negative 2, and we will shade that in and move all the way to the right. The last part about this is that we have not yet discussed the absolute value. And you remember that for every non-zero real number, x, the absolute value is always denoted by a symbol that looks like this. The absolute value of x is considered to be the positive number of the pair negative x and x. So, for example, the absolute value of 4 is equal to 4. Likewise, the absolute value of negative 4 is also equal to 4. Because remember, if we are discussing the absolute value, it's really referring to the distance from 0 on the number line. So that the absolute value of a number is never a negative number. And so the absolute value is always going to be, one way to think about it, the absolute value is always going to be a real number that is greater than or equal to 0. And it's also very easy to see that because you remember that there's something called the additive inverse, right? And so the additive inverse of a real number is negative, 0, or positive, according as the number, we should say it that way, according as the number is positive, 0, or negative. So you can actually restate the definition of the absolute value, and you can kind of label it this way. We're going to do, actually, I do want to do a proof of this. I'm not satisfied without a proof. So first thing is, we'll say is that the absolute value of x is going to be equal to x if, conditions, of course, if x is greater than or equal to 0. Or negative x if x is less than 0. So what happens is when you represent numbers as points on a number line, the absolute value, of course, is always, as I said before, it's describing the distance of the graph of x from the origin being 0. And so there's an interesting property that you've probably seen before. If you have let's say you had an inequality that was the absolute value of x being less than 2, just as an example. So what this really means is that since we're talking about the absolute value, this sentence, it's really a sentence, and we talked yesterday, if you watched the previous video, about conjunction versus disjunction. So this is only true if the sentence, if we consider a sentence negative 2 is less than x, and also x is less than 2, right? So it's in between those points. You can look at it that way. But oftentimes, this is only described to you, but it's not actually proven. So the general statement, the general rule is we have an inequality of a number, and we label it as negative a is less than x, which is less than a. And how do we prove that? How do we interpret that? Well, this is what we call a double inequality, right? So again, that means that negative a is less than x, and also x is less than a, right? So it's a conjunction. And therefore, we could split the inequality. If we split the inequality, it's the same as saying that, well, if negative a is less than x, then that means x is greater. That means that x is greater than negative a and x is less than a. All right? So, how do we verify each part? First, if we prove, first we're going to prove that x is greater than negative 8. We have to start with the assumptions of, or properties, if you prefer, of x relative to negative 8. So, for instance, if x is bounded, we say bounded between negative a and a by definition, then this inequality holds. And likewise, to prove x is less than a, we apply similar reasoning. It applies based on the bounds, the given bounds, we call it. So if both parts hold, we can combine the results into negative a being less than negative a is less than x and less than a. And if you provide an example here, one way you can look at this is if we let x and a, we can let that denote or represent real numbers. And what we could do here, we're going to say such that a is less than 0. And that means the absolute value of x is going to be less than a. But if and only if the condition holds. If and only if negative a is less than x is less than a. And so we've already said there are two statements here to prove. So how do we prove it in general, right? So for every x, and we're going to say x is an element, of course. Let's see where my symbol was. That should represent the real numbers. Then the absolute value, first of all, is going to be greater than or equal to 0. And we know that since a, in this case, is greater than 0, so that means that negative a is less than 0. And if that's the case, what can we do from here? That means that for every x, negative a is going to be less than the absolute value of x. Think about why that is. Why is that? Now, you have to first, if you consider the x's for which x is greater than or equal to 0, then for these, the absolute value of x equals x. So now you would have negative a is less than the absolute value of x, and the absolute value of x we said was equal to x. So that means that the absolute value of x is less than a, or, but if you use substitution, then we could say negative a, we go back to our rule here, to our statement. Negative a is less than x, which is less than a. So we get the desired result. All right, so this is a partial proof, of course, because you still have to consider those x's for which x is less than 0. So in those cases, if x is less than 0, then the absolute value of x is equal to, I should say, negative x. And so we have, again, the absolute value, if we just represent it by the negative a, is going to be less than the absolute value of x, which means that the absolute value of x is negative x. And of course, you could use substitution now. If you multiply, if you multiply by a negative number, in this case, let's say -1, you will get a being greater than x, which is greater than -a. Or you will get -a being less than x, which is less than a. So that is your desired result. So so this is a partial proof, but I wanted you to see why we do that. We do it that way, and we created that rule, and we create those rules. Let's do so a general principle. Another way you can remember this is that when you are dealing with inequalities that involve absolute values, you can keep in mind. You could keep it in mind this way. You could say that the absolute value of x is going to be less than a, and if that is the case, then you can say that -a is less than x and less than a. Alternatively, if the absolute value of x is greater than a, then you can think of it as x is either or. X can be either less than -a or x can be greater than a. So keep in mind these principles. I'll show you some examples that were given the other day and see if you can solve them. I want you to solve them before I do. I want you to think about them and see if you get the same answer. What if I gave you, for example, the absolute value? We're going to use set notation. What if we said the absolute value of x plus 1 and we could make that be less than 4? So how would you solve a problem like this? Take a moment using the principles that we've described and see what you get. Did you pause the video? I hope you paused the video and you tried it. If you got the answer as -5 is less than x, which is less than 3, then you are correct. So how do we do this? First, we have the absolute value of x plus 1 is less than 4. That means that we can subtract 1 from both of the inequalities. If you subtract 1 from both of the inequalities, you now have -5 less than x less than 3, right? And why is that? Because remember to have, you have to do it on both sides, right? So this means -4 is less than x plus 1. And also, remember we talked about disjunction versus conjunction. Also, it is less than 4 based on the proof that we did earlier, the partial proof anyway. It's a little bit longer than that, but that's just so you get an idea. Now you can subtract 1 from both sides. So now you have -5 is less than x, which is less than 3. And there you have a basic example. Let's try another one. What if you have the absolute value of 2x minus 5 and we're going to say that that is less than or equal to 1. So in this case, again, we have -1 or 1 there as part of our range. So we could say -1 is less than or equal to 2x minus 5. Which is less than or equal to 1. And now if we add, in this case, they're subtracting 5 in the equation, so we can add 5 to both sides of the inequality. And if we add 5 to both sides, we get 4 is less than or equal to 2x, which is less than or equal to 3. Right? Because if we divide on both sides by 2, actually, I skipped a step, but you should get 4 is less than or equal to 2x. Right? And that should be less than or equal to 6. All right, and so we divide by 2 on both sides, and we get 2 is less than or equal to x, which is less than or equal to 3. All right? But however, there is an example that I gave last week, and a lot of students were getting this wrong. And because again, they're not, once you start to see fractions in an equation, you start to become a little bit intimidated, don't you? No reason for that. The rules are the same. So, but they forgot a few things. The expression was, we said the absolute value of 1 minus 1 half x. And the way it was written was, I always use kind of the braces. And we have the absolute value of 1 minus 1 half x and we said that that was greater than 3. So, what do we do when you have an equation like this, when you have fractions in your equation? Well, this means that, once again, it's an or statement. 1 minus 1 half x can be greater than 3, or 1 minus 1 half x can be less than negative 3. So let's write them out. Right? Can be greater than 3 or less than negative 3. And if that's the case, then we have to be careful here, because negative 1 half x, if we isolate here, if we move the 1 to the other side and subtract, we now have negative 1 half x is greater than 2. Or, on the other side, we have negative 1 half x is less than negative 4. Now, remember we said, if you have negatives, we need to reverse. If you're dividing or multiplying by a negative, you need to reverse the inequality sign. So if we have here the denominator of 2, that means we have to clear this fraction by multiplying by 2. That means x is less than negative 4. Notice how we reverse the inequality sign. Or x is greater than 8. So if that's the case, you would write this, if you use set notation, assuming you don't have to graph it, you can use set notation, you use the union symbol. So that means that the solution set is X being, and always use braces when you're dealing with sets. So you could say X is either X is less than -4, and use the U symbol, or X is greater than 8. And there you have it. So don't be intimidated by fractions. The principles remain the same. However, what if you had an equation, let's say an inequality, that they were asking you for the absolute value of 3x minus 2, and I'm just going to write this one out. And outside the absolute value, we're going to have -1, and that's greater than or equal to 5. So in this case, you can move the -1 to the other side. So you have the absolute value of 3x minus 2 is going to be greater than or equal, I don't know why it's doing that, greater than or equal to 6. And that means that if the absolute value of 3x minus 2 is greater than or equal to 6, then that means there are two possibilities. Either or. 3x minus 2 is greater than or equal to 6. Or that means also 3x minus 2 is less than or equal to -6. So we proceed as we did before. We can add, in the first case, in the 3x minus 2, we can add 2 to the 6. And that leaves us with 3x's greater than or equal to 8. Or 3x is less than or equal to -4, right? If we add. So this means, okay, now we're going to divide by 3 on both sides. So we have x's greater than or equal to 8 over 3. Or you have to have here x's, if 3x is less than or equal to -4, we're going to have -4/3. So x is less than or equal to -4/3. Notice here I didn't reverse the inequality symbol because I'm not dividing or multiplying by a negative. It's still a +3. So here the solution set, we could say, is x is less than or equal to -4/3, and we can put the union symbol there, and x is greater than or equal to 8/3. So I hope that this clears up a lot of the questions that you had on inequalities. But if you still need assistance with inequalities, please let me know. There are also, just so that you're aware, there are also inequalities that have letters, uh, that you solve for a variable. In other words, like x over a plus b over a squared is less than 4x over a, etc. But I didn't do them in this video because these are the most typical ones. But hopefully the proof, the partial proof anyway, and the standards between video one, the first part of this series, and this one has helped you. If it has, please subscribe to the channel, keep helping us, and I appreciate you all. Thank you.